Professor Darpe has been a guest scientist at the Institute of Lightweight Structures, TU Dresden, in Germany from May to July in 2003, visiting researcher at Knowledge Center of Smart Machines, VTT Technical Research Center of Finland from May to July in the year 2009, and guest scientist at Cluster of Excellence at European Center of Emerging Materials and Process at TU Dresden, again from May to July in the year 2013. He has been a member of the Propulsion Panel of Aeronautical Research Development Board. Professor Darpe has been founder director of a startup company, Silver Knight Technologies Private Limited at IIT Delhi. And Professor Darpe is also a recipient of J.M. Mahajan Best Young Teacher Award, Erasmus Plus Mobility Award, and a life member of the Condition Monitoring Society of India. I'm sure, dear participant, with the immense experience Professor Darpe is having, you will definitely be benefited from his talk today. Thank you once again, Professor Darpe, and I welcome you to deliver the talk.
Thank you so much for your nice introduction. Really honored to be here. Ateeb, I'm so delighted to be here. I think there was a slight delay because my mic was muted and we were having some confusion. So my apologies for starting a little.
No problem. No problem.
Yeah. So if all participants agree, we can get started. Let me share my my slides and we get started now, I guess. Are you able to see the slide?
Yes, sir. Yes, sir.
Okay. So the topic of my first of the two lectures is bearing health monitoring from lab to field. So I shall, take you through some of our experiences in working with bearing diagnostics. It has been almost 12 years or even more than 12 years that we started this work. And so whatever little we learned through our experiences of working in the lab as well as field is something which I will share with you. And if you find anything not clear, please stop me then and there and kindly ask the clarification or question you have. So my name is Ashish Darpe. I am faculty at IIT Delhi, and we will get started with the topic. So the thing here is fault diagnosis or bearing health monitoring is basically a process through which an engineer sort of acts like a doctor and tries to gauge from a machine he is trying to monitor or is responsible for the upkeep and availability, is basically trying to gauge its health like a doctor tries to gauge the health of a person by looking at some telltale signs from the signals that it gets. So this picture basically summarizes what this whole field is all about, trying to understand from some symptoms the overall health of the machine and its elements. So here the person could be deciphering the signal for the health of the gears or bearings or rotor and so on. And as the machinery becomes complex, the job becomes tougher and more challenging. So the outline of the talk today is I will introduce this topic, some background, very brief background of it, why we should be actually concerned about monitoring the health of the bearings, followed by introduction to vibration-based bearing fault diagnosis, because there are multiple routes to getting the fault detected, but vibration-based monitoring is found to be much more convenient and is a de facto approach. Followed by that, what are various time and frequency domain approaches for doing this identification. A bit of time frequency domain alternative, which we implemented many places. Industry implementation of what we learned and developed at the lab scale. And of course, finally, we'll summarize. I would like to upfront acknowledge two of my best students who worked in this domain and has generated such a wonderful know-how in the bearing diagnosis. Dr. Piyush Shakya, who is currently faculty at IIT Madras, and Dr. Jaskaran Singh. Both of them have really put in excellent quality research work. Okay, getting started with the introduction as to what basically the diagnosis of this element, the bearings, and in particular the rolling element bearings. Of course, we will not be dealing with other type of bearings, but focusing mainly on rolling element bearings for obvious reasons that it finds its application right from simple electric motor to a rocket launch vehicle, a satellite launch vehicle. So it can be an important element in one of the most rudimentary or very simple electric machine to a complex aerospace vehicle, aerospace structure. So in the case of electric motor, it is supporting the rotor, and in the case of launch vehicles, it could be a liquid oxygen pump or a liquid hydrogen pump, which is supplying fuel to the rocket to the engine. So in some cases, the failure may be tolerated, but in the second application, as you see, you can imagine what will happen if the bearing seizes or it fails, if fails to deliver. So the consequences can be quite disastrous in some situations. It can find applications in machine tool industry, like these two are the two applications. The second one in which we actually worked quite extensively. In both of these machine tool applications, the bearings form a very critical element. And this is despite the fact that they are relatively cheap in comparison to the overall system cost. So despite being key machinery element, the element cost as such is not much, but despite being cheaper, the failure of that can be extremely costly because of several reasons, and we will discuss that. So the reason for that is the downtime is very costly in terms of the time wasted, in terms of product quality degradation. For example, in this case, you can imagine that a bearing here, if it degrades, will degrade the quality of the machining. Okay, there will be a lot of errors. The machining quality will get hit. And so you have more rejections. So even if it is not completely failed, it will influence the product quality, which ultimately leads to added cost. Excuse me. So this is one important reason for we to be careful about it. The other important aspect of bearing failure is if it gets undetected, it can lead to secondary damages. For example, if the bearings in an electric motor seizes or it stops working, it can have consequences with the coupling getting damaged, the shaft getting damaged, and so on. So there are secondary damages. If one component in a complex interconnected machinery fails, it has consequences, and therefore it can be extremely damaging. The obvious question many times arises is that if the bearings are designed as per their L10 life for maybe 10 years or 5 years, anywhere between 5 to 10 years, why should we be worrying about diagnosing the faults in the bearings? But it has been observed that even if the bearings as such are designed to last several years, and it so happens that these bearings do invariably fail much before their design life. And some of the common reasons is the failure of the seals, foreign material ingress, improper handling, improper assembly, and so many other reasons which are difficult to comprehend or taken into account during the design stage. So when the bearings are tested, they are tested in an idealistic condition, whereas in practice, the conditions are very different. So, for example, one of the system which we were involved very intimately is a grinding machine tool, wherein there has been a documented history of the bearings which are sitting somewhere here supporting the grinding wheel. They actually fail because of the cutting fluid gets through the seals and enters into the raceways, and that creates cascading effect of deteriorated lubrication leading to failure. So therefore, we cannot say that I install the bearing today and should look at it after 5 years. That's its design life. That usually is not the case. Yes, many times they do, in fact, outlast their design life, but there is no guarantee, and therefore, in such situations, particularly when the damage is not tolerated. For example, there are some very high quality finishing processes which are involved with some machines. They cannot tolerate, forget about the defect, they cannot tolerate the general wear and tear of the bearings. So therefore, damage identification is very important. The other aspect of diagnostics is that gradually majority of the industries are migrating to condition-based maintenance. So gone are the days of periodic maintenance, and when you want to implement condition-based maintenance, condition monitoring or health monitoring of bearings is the key part of that approach. So if you do not know condition monitoring of your machine elements, CBM cannot be implemented. So therefore, this becomes a sort of a prerequisite for the implementation of condition-based maintenance. So in fact, that is one of the key reasons for which we should be conversant with what are the approaches, what to look for when we try to monitor. And the last point is the earlier you detect any impending problem in the bearings, the better headway you have, or the lead time you have for planning for the CBM or maintenance action, and keeping the inventory available and so on. So untimely failures are minimized to a great extent if you can have early detection. So those are the reasons which are important to the bearing diagnostics as an activity. The typical failure in the bearings are shown here in the pictures. As you can see, the raceways are mainly getting damaged. So this is the damage in the raceway. This is the inner race. That is, I think, the outer race. And those outer races show a very severe damage. But we have seen that even a small scratch or a small spall here can lead to a changed vibration behavior. And in one of the industries which we were interacting with, the bearing clearance because of the wear and the degradation of the raceways, if the clearance increases from 3 micron to 5 micron, they change the bearings. So the point is, such is the level of accuracy that they demand, and therefore any small deviation from the healthy condition must be detected in time. So these are some of the failures that I was talking about. These are the actual pictures of the failed bearings from these machine tools. When the cutting fluid in the coolant, basically during the grinding operation, that coolant basically enters into the raceways of the bearing, they eventually damage by reacting to the existing lubricant there and degrading it, and then finally causing damage to the raceways. The kind of lubrication that is expected and designed for, that gets compromised, and then you have a failure. Sometimes that grinding dust enters into the raceways, and that the dust itself will be like a foreign material. Even a small quantity is good enough to cause serious damage to the raceways, and that leads to small damage pitting in the bearings, and that basically starts and it extends towards all areas of the raceway. The raceway, anyways, is a highly stressed component in the bearing, and that if is starts degrading, you can imagine what will happen gradually. The entire raceway gets spoiled. There is another important work we are dealing at the moment with one of the major industry nearby, which has, of course, this picture is basically a small prototype that we have in the lab. But it's basically simulating a multi spindle head. Does the drilling simultaneously on a component. And one of the challenge and one of the issues that is currently being faced by them is that if one of the bearings fail in this particular drill head, there is no way they can understand which particular bearing is to be replaced, and then they end up spending a lot of time in figuring out which one to replace. If they want to replace all of them, the remaining good bearings you are unnecessarily throwing, and so on. So if you are able to diagnose which particular bearing is at fault, it would be a great help in then cutting down on the replacement time and cost. And so therefore this is one of the examples which tells you how important it is to have an idea about how to diagnose. Well, we now look at what are various condition monitoring parameters. That means when you want to now monitor it, how do you monitor it? Okay, what physical parameter you use for monitoring the bearing health? And in that light, this is in general applies to most of the machine elements, so it is not very specific to bearings as such, but in general, you can have an oral indication, oral in the sense that you can listen to the machine element or machinery. And there are many times oral indications. So you hear the sound of the system and can detect whether there is an abnormal sound or a changed sound pattern or a sound behavior, which can lead to detection or identification of anomaly in the system. So in case of bearings also, particularly you must have noticed in automotive garages, the mechanic basically listens to your vehicle and can make out if there is a changed sound pattern. And with his experience, he can immediately catch whether the bearing is at fault. In fact, if the bearings are degraded to a sufficiently high level, layman can also figure it out. So there is nothing great about it, but if you want to catch it early, expertise definitely is required. Then in some cases, for some machine elements and in some situations, even the visual indication is possible. In bearings, of course, that part is not so useful. it's hard to get any indication from outside. But because if you get flaws in the rolling elements of the bearing, increased friction leads to a higher temperature rise, and therefore, beyond the normal temperature change, a higher temperature can definitely lead to some kind of an indication that the bearings may be at fault. So if you place your thermocouple on the bearing housing, and the bearing housing shows up higher temperatures, then definitely it's an indication. However, what actually happens is it takes time for it to rise. So typically what happens if the machine is frequently getting started and stopped, then you will find that the temperature, it takes time to rise. If you stop it a while, then it comes back, and then again it starts as you restart it again. So there is no monotonous. In contrast, if you plot the vibrations, no matter when you start, immediately after you start it, the vibration will show an increased level as the damage changes. So it doesn't need a heating period or a period for showing it up. So temperature, although is an important consequence of changes in the condition of the bearing, it is not that sensitive a parameter, or typically when the damage becomes large enough, it has influence on the temperature value. And then of course, we also have seen in our labs that it takes time for the temperatures to actually rise. And particularly when you are frequently starting and stopping your machinery, then maybe temperature is not such a convenient. I should not say convenient, because temperature, there is nothing more convenient than temperature, because it's a very cheap sensor, easier to place, but it is not so sensitive, as much sensitive as the other parameters. Then you have a wear debris. So if particularly for bearings which are like journal bearings or sleeve bearings, wear debris are more common, because then you can have direct metal to metal contact and the debris is more readily there. In rolling element bearings also, if there is a wear in the raceways, probably you will get some debris, but wear debris is not very commonly used for the bearings. It may be used for gearbox much more commonly, and in that case also it can lead to the detection of bearing failures within the gearbox, but then this is one possible condition monitoring parameter. But by and large, it is found that whenever you have a small deviation in the healthy condition of the bearing, vibration is one of the most sensitive parameter, physical parameter, that gets affected and influenced. And it is by far the most established parameter for diagnosing the bearing health. The other upcoming parameter, although I'm using a term upcoming, it's not that it was not there in the past. It has been there for more than a few decades, but has not received as much attention as vibration, because of some obvious reasons. The sensors are a bit costly. The subsequent signal processing is not well developed, and there are a lot of ifs and buts. Robustness is a challenge. So there are issues with this, but then articles will vouch that they are better than vibration parameters. So those are also the options available for you. And of course, finally, although I am putting this as one of the parameters, may not be so relevant with rolling element bearings, but as a general condition monitoring parameter, operational variables can also indicate. For example, if you are monitoring the condition or health of a pump or a compressor, the pressure, outlet pressure or temperature, or the power delivered, and all those are the operational variables. The changes in them can indicate some anomaly in the system. But as far as the bearing health is concerned, these are major parameters of interest. And out of that, if you look at the overall convenience, cost, and the sensitivity to a small change in the damage level, this is almost like a de facto parameter. Nowadays, sensors can be as cheap as 20,000, 25,000. And despite initial investment, they can they are so well established sensors that they are long lasting and can survive the industrial environment and can give you excellent output and sensitivity. So having discussed this as to why vibration is an important parameter to monitor the health of the bearing, I would like to dig a little deeper now and understand basically why vibration is something which is getting changed here. So I'm trying to draw parallel with a vibratory system, and we'll take this simplest machine, which basically has a bearing on both sides of the rotor. The rotor is basically supported on two bearings. And if we treat this rotor as a simple vibratory system, which we typically model like a spring mass dashboard system, why should minute changes in the bearing health should change the vibration pattern? So typically, if you model this rotor and bearings as a vibratory system, wherein the shaft and the rotor can be modeled like a mass, all those who have done the basic course in dynamics in mechanical engineering domain will agree that it is a simple spring mass system, or can be modeled like a spring mass system, with the here representing the bearing stiffness. So if the bearing is having some stiffness, that stiffness can be the bearing stiffness. Damping can arise out of the shaft internal damping or the fluid in the bearing. Of course, it is well established that the bearings offer very little damping, but as a matter of completeness, this spring mass dashboard system representing the rotor supported on bearings is shown here. With the excitation also, so what would be the excitation to this system? And before we talk about the excitation, let us write the governing equation now. This governing equation for this simple vibratory system will be a very common and very well known ordinary differential equation for this the response vibration response X when it is subjected to an external forcing function T. Now, if the bearings are all fine, with the assumption that they are actually represented by linear string, which in reality is not, but then still as a first cut analysis, we can still treat all these vibration parameters as constant coefficients. And then the common excitation source to this vibratory system is the unbalance in the rotor, which will always be there. Whatever residual unbalance that is left out, that is going to be the excitation source, and that excitation source to this vibratory system will cause it to oscillate and generate a simple vibration response. Because the excitation is harmonic with the rotational speed, I expect the response to be looking like this: a simple harmonic response with the frequency omega as 1 over t, or maybe 2 pi by t. So this period is going to be related to the rotational speed of the. Now, what happens if this bearing develops a fault? So I am showing you here a bearing and a small fault here in the raceway. So supposing that there is a fault here, the green colored patch, exaggerated. What actually happens is that as these balls roll in the raceways, each time the ball rolls over this pit or small fall or a damaged raceway, then it bumps to that and generates impulse, because a ball which is rolling over a flat straight surface, if it encounters such kind of a ditch, we all agree will generate impulse. And as more next ball rolls over, you will have a series of such impulses generated as the balls roll over these raceway pits. So as they generate impulses, those impulses basically excite vibrations. They can excite vibrations in the outer race. Similarly, they can generate excitation to the inner race, and because the inner race is with the shaft, this shaft can transmit those impulses through the rotor and to other elements. But if we look at these impulses which are generated in the outer race, and you may notice here the outer race is directly butting against the frame of the motor. So these impulses, short impulses, mind you, these are very short impulses, but they are good enough to excite vibrations, periodic impulsive loading on the frame to which the outer race is fixed. And now if I put an accelerometer on this frame of the motor, okay, and connect it to the acquisition device, then this sensor will give me an output which, in contrast to a harmonic response due to unbalance, would look like this, because now a series of such strong impulses are getting generated, and they generate these kind of changed vibration response whenever the ball interacts with any flaw, either a spall or a pit or even a thermal crack in the raceway. Such sharp impulses will generate a vibration in the frame that would look somewhat like this. So, in fact, what will happen is that this unbalance will get coupled with these impulses, and the overall response would look slightly different than what you are seeing here. But the point is, if there is no problem with the bearings, with the healthy bearings, more likely case of the vibration sensor recording the data is going to be this. Of course, this is much more idealistic. It will be, infected with some other noise, but more or less there will be a distinctly different response whenever such flaw appears in the raceway. So that is basically the basic philosophy of why vibration-based signals would catch a minute change in the raceway profile, and therefore such physical parameter will be of very important use to monitor the health of the bearing. In contrast, if you look at this, the temperature rise will be much less and will be very gradual. It will take a lot of time unless the damage is distributed and is of significantly high level. Then the temperature rise will be there. Similarly, the noise change will also not be significant in this case. So the point is, vibration therefore is found to be the most obvious choice for monitoring the health of the bearing. Now the question is, suppose we are also need to look at whether the outer fault is in the outer race or is in the inner race or in the ball. So you may check that this star, what you see on the outer race, if it represents the flaw in the outer race, as the balls roll past this flaw, there will be a repeated impulses in the response, which will be captured by a sensor put on here. Or if the flaw is is here, then also as the balls roll, they will also interact with this. And if you notice the frequency actually, the frequency with which this defect interacts with these balls is going to be lower as compared to when the flaw on the inner race interacts with the rollers. That can be geometrically proved. In fact, there are expressions which are derived which tells you how much would be the frequency of repetition of these impulses when the defect is in the inner race and when the defect is in the outer race. So, but there are more interesting things between inner and outer race. Although theoretically what you see there is that whether the defect is in the inner race or on the outer race, if the defect is of equal magnitude, then you expect to have similar level of impulses which are generated. But the problem comes, or an interesting situation arises when you have a constant radial load acting on the inner race, and that typically is the case. Generally, the weight of the rotor is significant, and then it of course will act radially downwards. So for all horizontal rotors, this radial load will create something called as a load zone, depending upon the clearance in the bearing. So what it actually does is it applies more load on the lower side of the bearing compared to on the top side. In fact, on the top side, in this area, the balls actually get relieved because of the positive clearance, which is typically there in bearing. And therefore, the amount of load that is there on these balls on the lower side will be significantly large compared to what you see at the top. So if the defect is on the outer race, because the outer race is fixed, and if it is in the load zone, it will generate significant strong impulses. So you may imagine that balls which are already compressed and stressed to a large value, as they pass through these defect on the outer race, and if you connect it to a sensor which is sensing the vibrations of this housing of the bearing, it will record the impulses which are equal in amplitude, because the position of the defect is the same load, and therefore you expect almost a similar strength impulses. However, you imagine that the defect is moving with the inner race as the inner race rotates. Again, that is one of the most common things, that the defect in the inner race is rotating, because inner race always rotates. You typically always have outer race fixed in the frame. So in this case, what happens that when the inner race defect which is moving here is on the load zone, you have a strong impulses generated. But now when you see this defect going up and interacting with the balls which are already relieved, it will generate very low or no impulse at all. So compared to this strong impulse, you will have much lower impulse here, and that lower impulse sometimes it may not even generate, and then you have a situation which is very different than what you have for the outer race. So typically then what happens is, because of the movement of the defect from this load zone to unloaded zone somewhere here, the impulses in the unloaded zone are much feeble compared to the impulses in the load zone in this region, if the defect is in the inner race. And that basically is the physics behind such interaction that we exploited and published a good article by making use of this phenomena and making use of the time frequency domain technique. So it's not just putting an accelerometer and then taking the data, and so you need to know the physics behind the working of the bearing and some of the insights to come up with a precise and more useful, robust identification approaches. So this is one of the interesting phenomena typical to the inner race defect, and which is in contrast to the outer race. So using that, you can classify the fault, and sometimes classification of what fault also helps in residual life estimation, because the algorithms or the model for a particular fault varies from the other one. So it can help in identifying which of the fault it is there. Now, what are the various identification measures? I mean, we have been just thinking aloud about what is causing vibration to generate. That's what we have discussed just now, that the bearing, rolling element bearing elements interact with the flaw, and so that generates impulses. And those impulses occur periodically at a definite interval of time. And all that can lead to specific vibration signature, what we call. So that signature needs to be tracked and identified from the overall vibration that is generated. You must make a note that when you put a accelerometer on the frame of the motor, it's not that you will get a pure signal, that's what we are showing there, but it will also catch in parallel simultaneously other vibration sources, like the frame itself will vibrate at its own frequency, and so on. But then if you know the signature, what to call, it's to add those features. Now, what are the metrics which we use for identifying problems with the bearing? One of the most simple one is to find out from the time domain data the RMS value or a peak-to-peak value of the signal. We will discuss that in the next slide. There are other parameters like crest factor, kurtosis, which can be used for tracking the health of the bearing. We'll discuss that again very shortly. If you look at the repetition rate of those impulses, we have theoretically expressions for finding out the bearing fault frequency. So those impulses which are appearing repetitively, if you find out what is the time of repetition of those impulses, then 1 over that time basically gives you the fault frequency. So if those frequencies appear in your frequency features, then you can be sure that there is a fault progressing in the system. In addition to these, there are other methods, shock pulse value, enveloping techniques, or high frequency resonance technique, spike energy, and acoustic emission parameters. Those are additional things which are also possible to use for diagnosing the bearing faults. So when you want to analyze the vibration signal, what I showed you, you can use different techniques for its post-processing and representation, so that the diagnosis becomes easier. You can unravel or dig out or extract features very specific to bearings, removing some of the other parameters or other influencing sources. So the most common one is the time domain, of which some of the parameters like RMS, peak to peak I have already mentioned. So if you want to find out the matrix from this time domain data, maybe I will figure out what is the peak to peak value of this time domain data, or I can find out the RMS value of this time domain data. I can also find out the kurtosis value and so on. So there are many other parameters which are typically used. That identification is relatively much simpler than the other parameters that are shown here in this picture, because if you want to convert this time domain data into frequency domain data, you need some algorithms to compute it. Although not a rocket science, you can always do it using standard codes available. The reason for getting frequency domain data from the time domain data is some issues with the time domain data. It does not offer you detailed insight into what are the composition of this time domain data. It only tells you overall level of the signal. So how much is the strength of the signal as such. But if the signal changes slightly, it is hard to figure out what is the culprit or what is changing it. However, if you represent the same signal in the frequency domain, you precisely know which frequencies are there. So the kind of repetition rate that I talked about of the repetitive impulses, which are directly linked, and this time period is directly linked to the kinematics of the fault, and therefore, if specific frequency like 1 by t is present in the signal, for example, if this frequency represents the defect characteristic frequency of the outer wave, I know that there is some issues with the outer wave, and if this amplitude grows over a period of time as I keep tracking, then I can be sure that there is something wrong. Now, if there are other more dominant frequencies present in the signal, which are typically not related to the defect and will remain static, even if this changes by 2 times, the overall peak-to-peak value may not change as much. Therefore, it would be difficult to track the progress of certain high-frequency components. And therefore, frequency domain technique is important for us. The reason for this is because the fault signature, as we call it, the fault signature is typically through this frequency composition. And if we have a specific frequency components shown up in this frequency domain data, then identifying a given fault becomes easier. I hope things are clear to all of you, and there are hopefully there is no problem in viewing what we are discussing here on the slides. I hope the slides are all clear to you. So Dr. Atip, can you confirm that things are, I mean, you are able to see and view these slides? Okay. So the third technique, which is time frequency domain, has one step more information, in the sense that it combines both time and frequency domain, and then you can see in this map the energy or the amplitude level is seen on the color. The time domain or the time information is preserved on the x-axis, and y-axis shows the frequency. So all the 3 parts of the information are simultaneously available, because in time we usually do not have much information about the frequency. In frequency domain, we have lost track of time at which these frequencies are present. So in bearing, how does this make an important requirement? Because as you must have seen that the high frequencies are excited for a very short duration of time, and then they disappear. So the energy sort of gets distributed throughout in time if you try to do the frequency domain transform. So if you want to catch the location in time at which these high frequency resonances are generated, then time frequency domain can be a useful alternative technique. So as I said, a typical time domain data from an actual machinery is shown here. We can see that apart from knowing the peak-to-peak value of close to 6, it really does not offer much information, except that there are impulsive data in it, but it's hard to extract any further information. So typically what is seen in or is talked about in the literature is the time domain data being the raw data. It is rich in its content. It has all the information hidden, but that information is apparently not obvious from only the time domain representation. So So we need to process this into other domains to extract useful information. So the output or the processing of this time domain data to extract some metrics to quantify the signal is like this signal is, you can use the expression for the RMS, and all of you are aware of how to find the RMS value. This is the root mean square value of the signal, which overall quantifies the energy level of the signal. Can be a useful parameter to track the health. And in our lab, in one of the unit where we first started exploring the vibration data for health monitoring, the running of that rig for a long duration in the heavily loaded condition resulted in the RMS showing this kind of a trend. So it does the simplest of these parameters that you can think of in bearing health was able to show a reasonably upward trend before the bearing actually almost failed. And so it can be used for tracking the health of the bearing, except that for more than half the period, it stayed almost close to a static value. It's only during the last 1/3 or so period, the upward trend started picking up. So maybe the RMS value may not significantly show up, but at least for the later period of its life, you can still use this RMS value, and it does show an upward trend. So RMS is one parameter that broadly can be used. The other problem with RMS is that whether the increase is because of the change in unbalanced condition or other faults in the system, or is it only because of the bearing problem, is not clear. It's not possible to find. So therefore, RMS although shows something going wrong, but that is not a final verdict on whether the problem is with the bearings or not. Similarly, the peak to peak value can also be used for trending. It has been found that if you track the peak value, it grows like this. The peak grows faster than the RMS, and therefore, if you take the ratio between peak and RMS, that ratio becomes stronger, or the amplitude, the magnitude of the ratio will become higher at much earlier location than what the RMS grows. So RMS will grow as of number of faults grow, and then the peak will grow faster. And the ratio crest factor was touted as one alternative to early indication of faults in the system. So from the time domain, pure time domain data parameters, you can use either RMS, peak, or crest factor also. Okay, so these are the common ones. And another fourth important parameter from the time domain data, that means we are not converting it into frequency domain, we are basically looking at the time domain data, is kurtosis. So this kurtosis is basically quantifies the peakedness or impulsiveness of the signal. So how impulsive the data is something which is represented, mathematically captured using kurtosis. So if you have short duration spikes in the signal, it gets properly captured by using kurtosis. So the expression, it's a statistical parameter. It's a fourth order moment. You can find this out by taking various samples of the response at different instants of time, and taking the fourth order moment of the deviation from the mean value, normalized with the standard deviation. And so these this particular parameter, because it which basically captures the impulsiveness, therefore can be used for faults such as localized faults or characteristics in the bearing. And because such localized faults generate impulses in the time domain waveform, this parameter is found to be theoretically much more sensitive as compared to the RMS or the peak values. Okay, theoretically one can show that this value is less than 3.5 for bearings which has normal signal, and the moment the peaking starts, it deviates and goes beyond 3.5 for flat bearings. However, one of our students, Dr. Jaskaran, has shown through simulation that all is not really perfect for kurtosis, because it also depends on several other factors that it can completely give erroneous interpretation. For example, if I take a single impulse for the entire time duration, the kurtosis value is almost close to 191. And if you have these impulses repeated in the same time span, the kurtosis drops to 20.5. So there has to be distinction between the number of impulses here, and so the time sample should be properly taken. If you have double the signal level, that means this impulse has larger levels, you don't gain much in the kurtosis value. Okay, so the peak amplitude growth is not really going to be responding into the kurtosis. If one of the impulse has a sudden change, maybe because of the shock loading or any other disturbances, that completely again changes the kurtosis value. So as you can see here, this signal and this signal is identical, except that one of the spike has grown to double or a slightly higher value. But with a slight change here, you can notice, sorry, not this one and this one. So with one of the spike is almost double the amplitude, the kurtosis suddenly changes. So if you have some background disturbances, kurtosis value can really become a problem to manage, because it might give incorrect interpretation. And one of the most interesting part here is that if this simulated simpler signals, if it is in fact some noise, and here what we did was to add some Gaussian noise into the signal, the kurtosis again significantly drops compared to this one. So 20.5 drops to 6.5, and that is actually expected because the mean value of the signal, even if that doesn't change, the noise basically causes significant drop in the kurtosis value. If you have a Gaussian noise with a single sporadic impulse, that means the impulse is actually not related to the defect in the bearing. Had there been defect, there would have been periodic impulses. So one single sporadic impulse also generates a similar kurtosis value, and therefore, if you take a solitary data and single reading and get the kurtosis of this, which is largely influenced by a sporadic impulse, not the impulse related to defect, you may be interpreting the signal or the value of kurtosis to be damage bearing, whereas it is actually not. So these are some of the issues with kurtosis, and therefore should be carefully used. But otherwise, theoretically or the fundamentally, it is a very nice statistical measure of capturing the peakedness in the signal or impulsiveness in the signal. Only thing that you need to do is to take care of such possibilities where the values can get skewed. So one possible alternative is to clean up the data, and also take the average values over a more period of time, so that sporadic impulses or any other disturbances are averaged out. So in one of the literature, you will find experimental data through which they have shown that although the peak-to-peak vibration value gradually increased, kurtosis showed much higher or much steeper, more sensitive evolution. But at the same time, as we discussed, it started dropping after a certain level of damage. So it's not a monotonous indicative parameter. That actually dropped as time progressed. And it is also because if you have a small spall or a crack or any other anomaly on the track, as long as it is the localized fault, what actually happens that initially these flaws, as they generate, will generate very large impulsive signals. But generally in bearings, what might also happen that the sharpness of these edges in the flaw will get eventually tapered off, and you might not generate as strong and sharp impulses as in the initial phase. So as the damages or flaws sort of wears out and becomes not sharp as they are usually at the beginning, or there are more of them at the distributed location, it is possible that the kurtosis value will eventually decrease from a higher value. And this particular literature also shown through experimental data, similar thing that is happening over there. So need to be careful in using kurtosis. Then the other alternate spike energy measurement, also you use a shock pulse method. The idea there is the fact that these impulses actually generate sudden impulse excitation to a vibratory system. Now this housing in which the bearing is housed itself is again a vibratory system, because this entire box will be having certain mass and stiffness. Not only these impulses excite resonances in this block, but the sensor which is sensing the vibration can also be, because all of us are aware that a vibration sensor itself is a vibratory system. Okay, so this vibratory system has, of course, a higher natural frequency, more than, let's say, 20 kilohertz or so. So these high frequency impulses, very short duration impulses, these impulses excite resonances either in the supporting structure, in the housing of the bearing, or in the accelerometer itself. So what typically is done through these measurement approaches is that they filter out all the low frequency components which could be related to the rotation effects or other non-linearities associated with it. So low frequency data is all filtered out, and you filter out only high frequency regions. So you put this signal through a band pass filter and extract only the natural frequency vibrations of the structure, which typically could be in several kilohertz in excess. All your general rotational related frequency components, they are all less than 2 kilohertz or so. And in fact, many times it is within the few hundred hertz. So once you band pass filter it, so generally I will show you a few more data from the actual measurement. So it all has all kinds of frequencies, and typical resonance region is few kilohertz or more than 8 to 10 kilohertz. So it basically extracts this frequency signal and then plot it in time. And using a peak-to-peak detector, some electronic circuits, you can quantify this natural resonance vibration, which is basically is getting excited through the flaws and its interaction with the rolling element. So this is one possible option for a quick measurement of the problem in the system. The only issue with these is that you need to understand which frequency to bandpass filter and so on. So once you tune it to certain system, you will have to redo it for other systems. So if you do it for one system, it works well. But for alternate systems, you will have to keep changing and exploring things. So it's not that simple as such, but still can work very well. Now, having discussed this time domain data related techniques, let us look at the frequency domain. Before we straight away get the frequency domain data, it is also interesting and important for us to understand what exactly the advantage of getting the data converted into frequency domain. So this is one very useful example of a mechanical system driven by electric motor, a blower here, which has its own unbalance, and depending upon which particular part is exciting the structure for its vibration, it will have its own unique frequency composition. For example, 2400 RPM is like 40 hertz of signal. If it is rotating at that higher speed, it will generate, the unbalance in the blower will generate a certain unbalance related excitation frequency. So it will have a frequency related to its own operation. If the bearings which are there, which is supporting the blower rotor, if these bearings are loosely mounted, that will generate a signal which is typically twice the rotational speed. The blades, if they have issues, the blower will generate what is known as blade pass frequency. So certain time domain data will have its own frequency characteristic. If the bearing here is damaged, a damaged bearing will have its own specific frequency signature. All of these combined together will generate a typical time domain data, might look like this. And it is difficult. You forget about this part. If you only focus on this part, it is hard to figure out what are the contributing components in this overall signal. But if you decompose this time domain data into its frequency composition, each of these frequencies contribution can be related to certain mechanical systems and elements, and also to specific flaws or faults or issues with those machine elements. So therefore, if you decompose time domain data into its frequency domain signature, identifying the offending part or contributing part and doing further analysis on what is going wrong will be much easier than only looking at the frequency, only the time domain data. However, the time domain data generally gives you a quick glimpse of the level of the signal. So if the level of the signal is suddenly changing to a larger values, even the time domain data can suggest something going wrong. But what exactly is going wrong is better understood if you decompose this into its frequency decomposition. So this is another example of a system wherein there are multiple gears in mesh. If you put a sensor and then acquire the data looks like this. The time domain data itself is, again, as I said, only gives you an overall picture of the strength of the signal, but hardly any information of what is contributing to it. But if you convert this into its frequency domain representation, then each of these frequency peaks can be related to a certain system in the machinery. So subsystems or machine elements, you have a specific frequency component relating to it, and therefore then a particular amplitude rising gradually as you train the data, it becomes easier for you to figure out what is going wrong. So the analysis becomes simpler when you have a spectral analysis done of the raw time domain data. So time domain data, as I have mentioned earlier, is very rich in its content because it contains everything, including all other extraneous noise and other sources. It captures as it is whatever that is being generated at that point, but may not be so useful or informative. But if you then do some initial pre-processing, if you convert this into a frequency domain feature, it becomes much more informative from the point of view of diagnosing issues or anomalies in the system. Okay, now let's get back to the data, vibration data that is getting generated from the bearing. And I mentioned that because of any problem or flaws in the rolling elements or in the track and their interaction, you have these kind of repetitive impulses. And through kinematics, you can figure out how much is, if this is rotating at n RPM, after how much time this particular ball will go past a fixed point on the outer race. And similarly, if the inner race is rotating, outer race is fixed. And if you have a flaw here, how much is the period of time when this ball goes past the same fault till the next ball comes and interacts with it. So all of that can be mathematically derived, and you have these expressions derived through the kinematic relationship. And all those expressions for the repetition rate converted into frequency are given here. So if you have a problem on the outer race, if there is a crack or a spall on the outer race, the balls will pass through these outer race and will generate the outer race defect frequency. If you have a problem with the inner race, it will generate this inner race defect frequency. So if you convert this into its corresponding frequency domain signature, you will have certain frequencies appearing in the frequency domain signal. So this is the actual data from one of our test setups showing time domain data and its corresponding frequency domain representation. From time domain data, as I said, you get to know the peak to peak value. Hard to find out any frequency component unless you really zoom and then look at it. But then even zooming may not be really sufficient because signal is not always so stationary as much. It becomes too tedious to extract in frequency information. The moment you convert using fast Fourier transform or digital, converting the analog signal to digital, and from the digital data you can apply any frequency domain conversion approaches. The most common one is the fast Fourier transform. So you get a frequency signature like this. So the same time domain data converted into frequency domain would look like this. Now this data is corresponding to a small defect in the inner race, and you can notice that the frequency, if I calculate this frequency from the data of the bearings, where n is the number of rolling elements in the bearing, this is the rotational speed of the shaft, this is the diameter of the ball, this is the pitch diameter, and contact angle. So phi is the contact angle. So based on all of this information for a given bearing, I can find out and calculate the frequency of the defect passage of balls over the defect in the inner race. And that frequency is turning out to be this, and that appears in the spectrum. And because it's not a harmonic variation of those, these are all impulses, so these impulses will generate higher harmonic components. So you will also get some higher frequencies of the defect in the spectrum as well. So from the time domain data, by using frequency domain conversion, I can get the picture clearer as compared to what it is in the time domain. And then if I keep tracking the amplitude of this frequency, I can, over a period of time, check whether the defect is growing or is it static, or it is how is that progressing. Based on that, I can take a call whether the bearing is further degrading or not. Sorry. So this is another data that I have taken from one of the test setups. You can see in this particular picture, if you can see a small slit made. So this is a defect which is actually created, and then the bearing assembled and put it in the system. And then we ran and generated the data. So this slit width is about 0.5 mm, and we progressively increased it. And you can see that the amplitude peak to peak are increasing as we increase the defect. So as I said, from the time domain data, I can definitely get some idea about whether there is a healthy condition in the bearings or not. And from the time domain data also, I can understand if there is an issue here. Interestingly, despite such periodic impulses, the defect has not really resulted in a very strong defect frequency. So it does appear its components also appear, and relatively in their amplitude. So getting the frequency domain data itself may not always help. These frequencies are typically buried in other frequencies which are also there nearby, the harmonics of the rotational speed, and some could be resonances in the. So things which we discuss in theory, in practice there are a lot of other issues, and this is some first learning got by actually doing things and analyzing it. The other alternative to getting frequency domain data is the high frequency resonance technique. So this high frequency technique uses resonance which is generated in the structure or even bearing. So, am I audible?
Yes, sir, you are audible.
Oh, okay. Okay. I had a message that there is a poor internet connection.
Yes, actually your voice was breaking,
okay.
But anyhow you are audible now.
Okay, thanks. So it uses resonance phenomena, and what it actually does is it makes use of generation of resonances in the support structure, these periodic impulses. And what actually happens is that those impulses are modulated by these resonations are modulated by the defect, because the impulses are periodically generated. It makes that modulation and effectively. So I will just give you a step in carrying out this high frequency resonance technique or envelopment, and then actually demonstrate that using an example. So what you typically do is similar to spike energy method, where you do the band pass filtering around the resonance condition, and then from that resonance high frequency data which you have chopped out of the total data, you do the inverse frequency transform inversion, which gives you the filtered data in time domain. And from that time domain, you basically get a signal which is modulated. Modulated in the sense the resonances, they act for a short duration like this. So once you filter out high frequency data, this high frequency data will appear repetitively like this. And then what you do on that is you envelop that signal. So you do the enveloping, create an envelope signal of this data. So why? Because the resonances themselves are not giving you any indication of the problem in the bearing, but this envelope, which tells you how repeatedly these are generated. Why? Because their repetition is related to the bearing problem. The vibration, high frequency resonance vibration itself is not any how frequently these impulse generated is an indication. So therefore, if I do the enveloping of this high frequency data and take the FFT of this, because by taking the FFT, basically what I get is this time gets converted into the useful frequency information, and therefore that modulating source, which is the defect, is then obtained. So on the time signal to extract modulating source, which is due to the defect in the bearing. I think all these steps will be very clear in the next slide, wherein I show exactly we do in the HFRD. So this is the signal before we actually filter it. It's a very broadband signal. As you can see, the FFT of the data shows a large set of frequencies which are generated. So you have medium frequencies and then some high frequencies, and the bearing structure resonance are typically and our job is to extract this frequency. So for doing that, what you do is you that filtering removes all the lower frequencies on this side as well as on the other side. So by doing this, I get time which retains only this.
Sir, sorry to interrupt you in between, sir, but your voice is breaking, sir.
Yeah, go ahead, please.
Sir,
Okay,
your voice is breaking, sir.
My mobile network, because the current network may not be really useful.
Okay, sir.
Let's see network that is. Okay. I hope I'm audible now, loud and clear.
Yes,
Can you
sir. You
confirm?
are audible now.
Yeah, my apologies.
No problem, sir.
So you have this bandpass filtered frequency domain data. I have chopped off and removed all the lower frequencies. Now what I will do is I will convert this signal in time domain. So basically, once I have bandpass filtered the data, just a second. Okay. So after having bandpass filtered this, what I do is I do the inverse Fourier transform so that this frequency domain data is converted back into time domain data. Now this time domain signal will have only high frequencies, okay, high frequencies corresponding to resonances. And of course, you may not realize that from this data, which is for a very large period of time. So I have zoomed a very short period of time domain data and looks like this. Now you can see that this signal has only high frequency. So you can see these are the resonances, periodic resonances which are excited in the system. So the signal itself is very high frequency, lower intimidating lower frequencies are all filtered out. Now what I do is I do the enveloping. So the red signal that you see in this time domain data, which is basically going over all the peaks of this signal. This is basically the envelope signal. Okay, that envelope signal is what I need, because what is envelope signal? This envelope signal is periodic interaction of the balls with the defect in the rays. Okay, so this information of this time period of repetition of these impulse generation is what I need. Okay. Now, how this signal is different than the original time domain data, our original time signal, is that original time domain data was also polluted by a lot of other low frequency contributions. So therefore, I was not able to make a clear distinction or a clear indication of what is happening. By filtering out the high frequency region, I am now in a position to focus only on defect induced high frequencies data. So now this red colored envelope signal, if I convert it into frequency domain, then I get basically a frequency domain of the envelope signal. And that frequency domain of this envelope signal actually gives me very distinct, clear presence of the outer race defect frequency. You can see how clean the frequency spectrum look like. Now that in contrast with the very polluted and polluted in the sense a spectrum which was having so many frequency components. You can see that so many frequencies are there, and the actual defect frequency gets buried in the signal. So if I do that using this high frequency resonance technique, I get much clearer picture and better information of the defect in the bearing. That's what I have got here. Okay. So this is what is known as HFRT or enveloping method. Now we applied this enveloping method to an actual test data, and we were working with one of the industry, bearing manufacturing industry, and their accelerating test setup we use for seeding defects in the measured quantity so that the output can be correlated to the defect size. So these bearings were placed in these housings and then tested, and we placed the vibration sensors there, and the defect were actually seeded in a measured quantity, as you can see here, and different levels of damages were tested. So all of that for both inner and outer race defects, and then you can get the data. So we first started with time domain parameters. So you can see that as the damage size increases, there is a gradual rise in the RMS value. Okay. So as I was mentioning, the RMS value does show rise as the damage increases, but you can see that the initial change is very marginal, and then only with very large values it picks up. Same happens with kurtosis. It grows a lot. Crest factor was not so significantly changing, but it was also plotted, and you can see that as the damage increases, there is a distinct increase in its value. So the time domain data also can be used. How sensitive it is, it's a matter of question. Now, we also looked at the frequency spectrum of the healthy bearing. So every time, if you only look at the defective bearing, it can lead to incorrect interpretation. You should always keep on comparing it with the healthy bearing. So this is the data, the frequency domain data of the healthy bearing. What you notice here is many harmonics of the rotational frequency. This is the rotational speed related frequency. Harmonics of them, they do appear in the spectrum. It is expected in reality. Bearing itself is highly nonlinear element from the vibration viewpoint. So there will be some higher frequencies which will always generate. But the defect frequency, except the outer res defect, is not expected, and it does not appear. So these are the spectrum for the outer res defect in the full span, 2.25 kilohertz up to 0 to 25 kilohertz. So let me just tell you the outer res defect frequency, I think, was close to 150 or so. So that is really not there in the outer res defect, in the healthy condition. So no defect frequency appears here. When we change the defect size, look at these are progressive increase in the defect size. What you can notice is all the y-axis limits are identical. What can be noticed very clearly is the energy at high frequencies is almost non-existent here, and a very large resonance region here. So the energy slides into high frequency region as the bearing deteriorates. And this has been mentioned in the literature that higher resonances are excited as the defect grows. So you can see that gradual increase in these high frequency regions is quite well noticed here. And the same happens with the inner res as well. And therefore, the HFRT can be quite nicely applied here, wherein you can identify these resonance regions and apply bandpass filtering and all subsequent process. So what you see here is the frequency spectrum in a zoomed area. Look at the outer res defect. This A represents the defect frequency. So it is very little in the beginning, grows with 1000 micron defect size. It grows further here and then comes down actually for a very high defect level. So you may see that these defect frequency amplitudes are all flanked by much higher other frequencies not related to the defect. So same is with the inner res. You can see that inner res defect frequency like this A is appearing, but they are all of lower order of magnitude. And this is something which is very interesting to notice, that in practice, the frequency domain data may not be as expected or cleaner as you expect it to be. But when you use HFRT, this is what we obtain. An outer res defect data, when you apply HFRT to that data, very clean spectrum, no trouble in interpreting the data. So very clean, consistent, increasing amplitude. You can check with defect size, absolutely picture perfect outcome from the high frequency resonance technique. For the inner res defect, we get reasonably clear data, but what we observe that other frequencies also clamor for attention. But then you should also understand that we discussed right in the beginning that the inner res defect, the impulses get modulated as the defect goes from the load zone to non-load zone. And what you are observing here is a very rich modulation features, which are actually indicative of the inner res defect, and it's actually be useful for fault classification also. So when I say inner versus outer res defect, for the same defect level, this is the difference between the outer res and inner res, and which is actually because of this kind of modulation in the strength of these impulses in inner res, and the absence of it in the outer race. So this is something which is very nicely captured here from the actual experimental data on the lab setup. So the modulations which are there on amplitude modulation of these impulses because of the migration from load zone to non-load zone is actually reflecting in the side bands which are created or generated. So you have B minus and plus. So this is defect frequency. This also is the second harmonic of the defect frequency. This is the first harmonic of the defect frequency, and this is separated by the side bands which are due to the modulation. So the difference between these two is the rotational speed. Okay, so the sideband generation is a very typical signature of the inner race. So from the HFRT data, you can actually diagnose whether the defect is inner race and outer race or outer race. Of course, the frequencies themselves tell us whether it is inner race or outer race, but the modulation character also is a second level confirmation that the defect indeed is the inner race. Then we made a comparison of all these parameters that we investigated for how sensitive it is to the defect size. So what we plotted is the increase or not of these parameters. So we ran for a particular defect size. We ran it for a large period of time so that we get a very large set of data for the same defect size, so that a more or less equal value we expect for the same defect size when we run it for a larger period of time. And as we increase the defect, whether this amplitude grows so that we can say that the parameter is sensitive to the defect growth. For that purpose, all of these investigations were carried out. So you can see peak and RMS, both of them are growing nicely with the defect. The crest factor is not as sensitive. Kurtosis, yes, it showed because all the time the defect was fresh. But the defect frequency from the FFT was not really sensitive, you can notice here. In fact, it dropped for very large values. But look at what is showing up for HFRT. HFRT was able to show a very steep rise as the defect grew. And by far, we found that that was one of the best parameters to monitor. Then other parameters, as you see here, they are all there. For any detailed understanding or further reading, you may refer to this particular paper to know more about it. Now, we did this lot of investigations on the bearing from a state-of-the-art test rig setup in the lab, wherein we used all kinds of sensors to extract the information. We also used data fusion techniques, so multiple data or multiple features like RMS, kurtosis, crest factor, defect frequency, HFRT data, and time frequency domain. All of that can be fused using an approach called as the Mahalanobis distance. Unfortunately, we are, in this first lecture, it is difficult to cover everything, but you can refer to our papers on the Mahalanobis distance. What we have shown is if you fuse relevant parameters into a single composite parameter, it gives you much better information about the trend of the degradation of the bearing. So this is from this particular test rig. We ran to failure one of the bearings, and this is the data that we have. The RMS and the peak values were not very sensitive or not showing up as much increase as compared to the Mahalanobis distance. So one can then start looking at alternate and more advanced level approaches to make the system much more robust and more sensitive to the defect progression. We did make a ranking of how well the parameter pertains to its progress or the change as the damage progresses in a bearing. And these are all the rankings. You can see that although FFT is suggested, but FFT itself, bare FFT, does not really give a good parameter of interest. Instead, HFRT and Mahalanobis distance and kurtosis, these parameters are better compared to the others. So these are the confirmatory additional data sets, and it's this thing that I will skip at the moment. We'll now look at the most important part of how we made use of these learnings to implement these systems in the field. So one of them was from one of the funding agency in the defense and aerospace sector, who actually wanted to develop a diagnostic system for their turbopump bearings. So this is a prototype booster turbo pump, which was given to us to explore and develop this system. And we set it up, took the data from, so the turbo pump of this kind operates in excess of 40,000, 50,000 RPM. And so you can see that it was set up in the lab, and it ran with some seeded defects in the bearings, and the data was recorded, speed was recorded, and what we obtained, the FFT spectrum of the defect with the outer rest, you can see that, for this speed of 30,000 plus RPM, the defect frequency is almost non-existent here, despite the fact that the bearing had a defect, somewhere here also in this case. But when we used HFRT, you can see that outer race defect frequency is conspicuous. It's very much evident there. Similarly, for the other speed data, outer race defect frequency is very strongly appearing here. And that actually gave us a lot of confidence that the end user was actually using FFT spectrum, and we have shown that it is indeed difficult to extract defect information from bare FFT. So by doing other alternate processing, we have developed this front end for the diagnostic system, and this entire thing was implemented in field there, which gives, of course, the multiple indication of how the parameters are varying in the actual setup there. Yeah, so everything was online health monitoring system was developed and delivered to the user, along with some additional software for processing the vibration data. The other fallout of this entire work was development of bearing quality assessment system for one of the industry partners, wherein a fresh bearing, when it is manufactured, has an inherent manufacturing tolerances related issues. That means the raceways, even if they are perfectly manufactured, manufacturing tolerances will generate waviness in the raceways and other issues. They all will lead to undesirable lack of quietness in the bearing. That means there will be some noise which will be generated because of the waviness in the raceways. So there will be no traditional or a conventional fault which will be there in the bearing. The bearings will be perfect, but there would be waviness or roughness induced vibrations, and those are picked up by sensitive instrumentation. And so basically they wanted to replace some of their earlier old machines which were based on some earlier technology. So we developed this entire measurement and processing system for them to assess the quality of the bearing from extracting and processing the vibration data. So all what you see here is you see a sensor which is tracking the outer race as the inner race rotates, the vibrations of the outer race are picked up from there. The signal takes it to the data acquisition card and then sent to computer where the software developed for processing the data does all the processing and flashes out the um, um, entire diagnostics of the bearing in terms of its RMS value, kurtosis value, and because these are all generating higher frequency noise, so we pass it through different frequency bands and extract band level values and then do the processing on that data. If you want to change the bearing type, you can do that accordingly. It automatically calculates all the defect frequencies and some of the other information. So all that was actually developed and delivered to them. This was one of the major projects where Dr. Shakya worked with us, and his efforts, we could develop our indigenous diagnostics and prognostic system with the industry partner developing grinding machine tools. So what you see is all these sensor data is processed, and then apart from the diagnostics of what the current health of the bearing, we also have developed the life prediction algorithms and so on. So all that was actually the culmination of the initial level lab-based measurement and data analysis that we started with and resulted in a good quality work. So this was actually implemented, demonstrated in the actual machine tool. This is the front screen, how it looks like, and was also demonstrated and exhibited at an exhibition way back, of course, in 2016. So this is our bearing health monitoring system connected with one of the machine tools, CBN machine tool, the grinding machine. Okay, I think we have 5 minutes left. There was a topic on the time frequency, but then I would prefer that in the last 5 minutes, if there are any questions based on whatever we have discussed, it will be better than completing another small part. If there are no questions, I will.
Yes, sir. There is a question from Anirban Mitra. That is amplitude on a combined time domain plot the sum of all the amplitudes?
No, it is not necessary. That was only a pictorial depiction. The amplitude will not be a sum total of all amplitudes, obviously, because with frequency changing, their peaks will not add up algebraically. So it's not. It is that time in that particular slide which you probably is referring to is only a pictorial depiction. It will not be a summation as such. It will not, because there is a phase which comes into picture. Yeah,
yes,
because the phase will come into picture. So it was only to mention that all the frequency components will add up as such. They may not add up together in time. So all of these, although they are showing 1 micron each, does not mean that it will sum up to 4 microns. Therefore, it is showing that it is approximately 4 microns, not exactly 4 microns. Because amplitude of this particular frequency component will be at this time, whereas this amplitude will be at some other time. So they will not, in fact, add up to 4 microns. It will be less than 4 microns. Is that clear?
Okay, sir. Okay, I hope his question is answered. And sir, there is another question from Muhammad Atif Jamil. He said that he's working in the area of fault diagnosis of ball bearing using machine learning, where the primary concern is the classification of faults. So he said he said that you must have also mentioned in your lecture that the identification of fault type helps in mathematical modeling. But people often say that the diagnosis or particularly the classification of bearing faults is not much significant. The bearing has to be eventually replaced once it gets faulty. So more emphasis should be put to the prognosis and RUL So he basically he wants you to comment on this.
Yeah, his point is right in the sense that from the industry perspective, this is often the case where people are not really interested in knowing whether the ball is at fault or inner race is at fault and so on. However, the comment that I made was in the context of overall machinery prognosis, wherein if you have a complex machinery containing multiple elements, and for example, if you have gears, if you have bearings, if you have other components, then identifying which particular fault is at is referring to which particular element helps us in figuring out the whole system as a whole. What is the RUL for that? In addition to that, even when I talk about the inner race and outer race separately, the frequency with which the inner race is getting interacted is higher than the outer race. So over a period of time, a fault might grow faster in the inner race than on the outer race. And your RUL prediction models typically are fault. They are not fault independent. That means they have a strong influence on what fault you have for finding out the RUL of an entire bearing as such. So in that context, if you know which fault is has been generated, maybe of use. Regarding AI ML techniques, I mean, there is absolutely for that kind of techniques, the fault and the location of the fault may not really matter, because everything is properly what should I say, is properly trained based on the from the simulated data or the data from the measurements. So nothing comes as such from the physics of the problem. Okay. So partly what he said is correct, that in the industry, the industry typically are not much concerned about where the fault is going to lie. So from the diagnostic viewpoint, it may not really matter. But from the prognostic point of view, I consider that it really matters. It may not be so apparent with bearings, but like in gears, it will definitely matter what kind of a fault is brewing up in the gears. And because the fault models and the growth models can be different at different locations, depending upon where it is appearing.
Okay, there is another question, sir, from PSS Murthy. He wants to know that what can be done to apply the condition monitoring for avoiding the mishaps of helicopters, as happened recently to our army chief.
Very complex question. That yes, there are huge impetus in monitoring of aviation critical equipment in avoiding these kind of accidents. For example, in tomorrow's lecture, I will give you an example of a similar helicopter crash, and it happened because the gearbox, which was the culprit, was not monitored, and subsequently all the helicopter fleet in one of the Western country are being monitored through these kind of techniques. They call it as health and usage monitoring systems. So they are indeed getting into the maintenance domain, where online health monitoring of critical components such as bearings and gearboxes and other equipment are indeed getting monitored. We don't see them often because the criticality or the cost may not be that high. But in aviation sector and aerospace industry, gradually you will see in future more and more such equipment completely wired, censored, and monitored in real time. So what is being contemplated is during the flight itself, for let's say a commercial airliner, during the flight itself, from the continuous monitoring of the data, the pilot is alarmed as some issues happening in the system, and then that information is relayed to the ground staff, so that the ground staff is ready with with the equipment, if the diagnosis is done during flight itself, so that appropriate equipment and marshalling of resources is done in quick time, so that you don't need the diagnosis to be done after it lands and it goes to a hangar, losing a lot of time. So therefore, in-flight, online, real-time monitoring is definitely going to come in future. Did I answer?
Yes, sir. Another question is from Praveen Nagesh. If the defect is in rotor, does it affect the bearing signature?
If the defect is in the rotor, see, the rotor defect will give rise to its own signature. Okay, and I don't think a defect in the rotor as such directly will influence the bearing defect, because the bearing is responding to the interaction of the rolling elements with the damage therein under the load from the inner race through the shaft. So both of them will independently appear in the signature.
And another question from Dr. Shankaran. He's saying that misalignment of main rotor blade in helicopter comes under which part of the component?
Come again? I just could not understand.
Sir, misalignment of main rotor blade in helicopter comes under which part of the component?
Which part of the component? What is meant by that? I'm not clear with the question itself.
Dr. Shankaran, can you be more specific?
Maybe he can be more specific in asking.
Can you be please more specific with your question? Meanwhile, sir, we can take another question from Praveen Nagesh. Does the sensor position affect the judgment?
Definitely, yes. Definitely, yes. We have a lot of work already done. I think Dr. Piyush Shakya must have discussed that here in yesterday's lecture. Sensor
Yes,
position does help. Typically, we expect, or it is advisable to put sensor in the load zone. And in many cases, like in gearbox also, we have proved and shown that the orientation and the location of sensor does play its important role. So we need to place the sensor appropriately, so that and as close to the bearing as possible, so that the influences of other vibratory components, like if you place it on the top of the at a location away from the bearing housing, you will catch other influences much readily. In terms of bearings, it has to be in the load zone in the bearing housing, as close to the bearing. Otherwise, you not only get, the transfer path becomes more complex and distant, reducing the strength of the signal as well, right? So sensor positioning and sensor orientation both are important.
Okay, sir. So since Dr. Shankaran has not written anything, and sir is also having another lecture, maybe I believe tomorrow.
Yeah, I have.
So
Maybe they can write to me. They can speak. They can come back to me on that also tomorrow.
Yeah. So if any participant is having any question, he or she can ask the questions in the next lecture, where maybe tomorrow. Okay, sir. So on behalf of the organizing team, I want to thank you, Professor Darpe, for such an enlightening and information-rich lecture, wherein you have given a deep insight into the topic. And sir, especially the graphics and the figures you used in your talk made it more engaging and convenient to grasp. And this was only possible with the level of experience and expertise you have. And it was a complete honor for me to listen to your talk, and I thoroughly enjoyed your talk, which, by the way, I'm sure everybody listening to you must agree with me. And I hope you also enjoyed your time with us. And maybe very soon, when this COVID thing is over, we want to see you here at Aligarh Muslim University. We welcome you, sir, to this. to our university.
Sure, it will be great honor to be there with you, and definitely we look forward to meeting in person. And if the participants or any attendee have any questions, feel free to send it either through you or to me directly, whatever, and then I'll try to answer that. And of course, we are meeting tomorrow for the next lecture. So I think thank you so much for inviting me and giving me an opportunity to share this, whatever little we know of this particular topic, and look forward to meeting you again.
Okay. Thank you. Thank you
All right.
once again, sir.
So thank you so much. Yeah, can I log out now?
Yes, sir. Yes, sir. Sure.
Yeah. Okay. Thanks. Thanks a lot.
Okay.